Now, the magnetic field, you have to know the magnetic field strength, etc. due to a magnet. We have already discussed that what is magnetic field. Magnetic field is the region which a magnet experiences a force. If there is a magnetic field here, then you can say if we place here a magnet, then the magnet experiences a force. And magnetic field in the space around a magnet, and that magnet can be produced by a current. Right? That's why you have to define the magnetic field in the space around a magnet or current carrying wire, within which its influence can be experienced by a magnet. Right? If here is a magnet, then there is a region, there is a space in which a small magnet can experience a force. If it is a current carrying rod, then there is also a magnetic field. That means then there is also a space in which if we place a small magnet, then that small magnet experiences a force. Right? And this magnetic field can be represented by some lines. These lines are not real, but are drawn to simply visualize the magnetic field. There is no line. Here is a magnet, then there is a magnetic field surround this magnet, and then that magnetic field can be represented by a set of lines. But actually those lines do not exist. Just to visualize, we can draw those lines. Visualize what? To visualize the magnetic field. Let us say this is a bar magnet. This is North Pole, this is South Pole. Then this is strength is Qm, strength is Qm. This can be taken as positive, this can be taken as negative. Field lines are like this. You can draw much more better. These are not completed field lines. You have to put arrows. Arrows will be like this. See here, we have drawn some field lines due to a bar magnet or other magnetic dipole, and the magnetic field lines of a bar magnet, and also this is the field lines for a solenoid also. The magnetic field lines of a magnetic dipole or a bar magnet or a solenoid form continuous closed loops. See here, continuous line. These are continuous closed lines traveling from North Pole to South Pole outside the magnet. But inside the magnet, these lines are from South Pole to North Pole. Outside the magnet, it is from North Pole to South Pole. But inside the magnet, it is from South Pole to North Pole. Remind Remember this thing. This differs from electrostatic field lines. Electrostatic field lines are what? They do not form closed loop. They emits from positive charge and goes to infinity or ends at the negative charge. Tangent to the field line at a given point. Tangent to the field line at a given point gives the direction of the net magnetic field at that point. That means if we draw here a tangent, then that tangent gives you the net magnetic field, direction of the net magnetic field at this point. Clear? If we draw here a tangent, then this direction of the tangent gives you the net magnetic field at this point. This is the property, second property. Third, you can say the larger the number of field lines crossing per unit area, the stronger is the magnitude of the magnetic field. Stronger is the magnitude of the magnetic field. See here, in this region, in unit area, larger number of field lines crosses. If we assume here unit area or a particular area, then number of field line crossing that area is greater than this. If we assume here is 1 meter square area, then the number of field lines crossing 1 meter square is greater if we assume here 1 meter square of area, right? Rather we want to say that the number of field lines is greater in a region, or rather you can say the number of field lines crossing per unit area is greater, then stronger is the magnetic field. If it is less, then feeble will be the magnetic field. Now magnetic field lines do not intersect. Two magnetic field line never intersect, as was in the electrostatics. If two magnetic field lines intersect each other, then at the point of intersection there will be, you can draw two tangents. That means in that point there is two direction of the magnetic field, which is not possible. Clear? So you can say two magnetic field lines do not intersect. Clear? Another property you can say that magnetic field lines dilate laterally and they contract longitudinally. That means in longitudinal direction, the field lines wants to contract, which shows that, see here, it in the external region, outside the magnet, it starts from North Pole, ends at South Pole, right? North Pole, South Pole. That means North Pole attracts South Pole. Then what happens? Then it tries to contract, right? And laterally, see here, separated. Why? Because like pole repels. That's why you can say that magnetic field lines dilate laterally and they contract longitudinally. And about this magnetic field line, you can say one or two more words. That uniform magnetic field line. Uniform magnetic field line or uniform magnetic field. What do you mean by uniform magnetic field? We can say a magnetic field is uniform. It does mean that each and every point in the region, the strength of the magnetic field is same and direction of magnetic field is same. If in a region each and every point has the same strength of magnetic field and the magnetic field has the same direction, then that magnetic field is called uniform magnetic field. And uniform magnetic field is represented by equidistant set of parallel lines. These are parallel lines and equidistant. Distance between two parallel lines is same. Then this field is uniform magnetic field. This is uniform magnetic field. Clear? Uniform magnetic field is represented by equidistant parallel lines. And there is also non-uniform magnetic field. Magnetic field in a region is non-uniform if it has different strength at different points or it has different direction at different points. Clear? Non-uniform magnetic field lines is represented by converging lines, diverging lines or unequispaced parallel lines also. This is non-uniform. This is also non-uniform. This is also non-uniform. Non-uniform magnetic field can be represented by this type of field lines. Now see here, in this region, number of field lines crossing through unit area is greater than this region. Here, see here, in this region, number of field lines passing through unit area is greater than this region. See here, in this region and in this region, the density is different. That means magnetic field strength is different. Strong magnetic field is represented by close spaced lines, whereas weak magnetic field is represented by